Let's look at another really important concept in having to do with vectors. Easily simple, just as simple as vector addition and lots of other stuff that we've done, but it turns out to be very crucial. And that's the idea of scalar multiplication. So let's say we start with a vector, and again, for simplicity, I'm going to start with a vector in 2 dimensions. Everything I'm going to say works exactly the same for 3 dimensions, just more difficult to draw. And let's pick a number, any number between negative infinity and infinity, so any scalar. Okay, so I'm going to define the product, the scalar multiplication or the scalar product of k and v as the new vectors, which has as components kv1 and kv2. So all I'm doing is I'm taking each one of the components and multiplying it by k. Right? Now, what's the geometric interpretation of this? What's going on here when I'm multiplying it by k? So let's see, if I'm starting from this vector v, and if I multiply by some number which is greater than 1, then the effect is to basically increase both components by the same factor, so it keeps the slope exactly the same, but makes it longer. And of course, again, I can move that vector, that geometric representation of the vector, somewhere else. Now, if I pick a number which is between 0 and 1, again I get a vector which is with the same direction, but this time is going to be shorter, and I can move it somewhere else. What if I use as k a negative number? Well, what's going to happen with the negative number is that it's going to reverse the direction. So everything which was positive will become negative, and anything that was negative will become positive. But notice that the slope is going to be exactly the same. kv2 over kv1 is going to be the same as v2 over v1, no matter what I pick for k, even a negative one. And again, I can move that one somewhere else. Remember that these are all geometric representations of the vector. The vector is just a pair of numbers. Now, in 3D, once again, the definition is the same. We're multiplying each component by the number k. It's just more difficult to draw. So I'm going to try and stay as much away from it as possible. Okay, let's stay with this idea of scalar multiplication just to show you the first result, the first interesting piece of information that we can get totally algebraically and in a way that in fact does not depend on the geometry, and that therefore we can use later on once we start to generalize all these vectorial ideas to more complicated things. What we're going to look at is the following. If I try to compute the length of kv, well, by definition, what is it? It's the square root of the first component, kv1 squared, plus the second component squared. Well, I can use a little bit of algebra and change that to k squared, which will be a common factor, times v1 squared plus v2 squared. But the square root of k squared is just the absolute value of k. Remember, the square root of the square of a number is not the same number, it's the absolute value of that number. And what is the leftover piece? Well, by definition, that's just the length of v. And therefore, what we have here is the first algebraic property that we obtain purely algebraically, property of vectors, namely that the length of k times v for any vector v and any scalar k is going to be equal to the absolute value of k times the length of v. This may look like a simple thing, simple to prove, simple to use, but it will turn out to be quite useful and quite interesting later on. Now, in 3 dimensions, again, everything works at exactly the same way. In fact, I encourage you to try going through the same steps in 3 dimensions. Not much changes, but it gives you a good idea of what is going on algebraically. Let me show you a simple example just to have a look at what these concepts that we have seen look like in a very simple situation. So let's say we have the vector 3, negative 3, and I'm going to draw it there. Remember, I can draw it anywhere if I'm just looking for a geometric representation. So I'm going to draw it there, and you'll see in a minute why. So I'm going to draw it so that the tip is at the origin, not the tail as we normally do it. And then I'm going to add to it the vector 4, negative 1. This time I'm going to draw the vector 4, negative 1 starting at the origin. And now you can see why I drew the first one the way I did. Because now if I have to add those two, remember, all I need to do is construct the new vector that, using the triangle rule, starts at the tail of the first one and ends at the tip of the second one. And of course I can do that algebraically, that gives me 7 and negative 4, or I can do it geometrically and you end up with an arrow that has exactly the same components, 7 and negative 4. What if I look at the length of the vector 7, -4? So that's how long that vector is. Well, I can do it algebraically. So that's going to be the square root of 49 plus 16. Are you with me? Remember the formula? Okay, if you don't, you may want to back up, review the formula, and then check that this value is correct, which turns out to be the square root of 65. Is that right? Well, square root of 65 is approximately 8. What you may want to do is check, maybe just pause and check that in fact this vector, the blue vector here, has a length of exactly, or not exactly, but of roughly 8 units, a little bit more than 8 units. What about if I want to consider the vector 1/2 of 4, -1? This is a scalar multiplication, a scalar product. So what I have to do is simply multiply the numbers together. 1/2 times 4, 1/2 times -1, that gives me 2 and -1/2. So if I draw that 1, I end up with that vector. Check that in fact the components are right. And notice that this vector has the same direction as the original green vector. It's only shorter because I multiplied by 1/2. What if I look at -2/3 times 3, -3? Well, doing the arithmetic, that gives us the vector -2, 2. And once I draw it, notice what happens. Again, this new vector is going to have the same direction as the old red vector, the vector 3, -3, but it goes the other way around. That's because we multiplied by a negative scalar. And here is another very interesting concept having to do with vectors, and one which is going to be the bread and butter of most of the stuff we're going to be doing later. Again, it's a simple concept, but one that I really want you to become familiar with. So, what is the concept? The idea is this following. What we want to do is we start from a bunch of vectors. Let's say we have a number of vectors, v1, v2, v3, vm, and it doesn't matter whether they're 2D or 3D vectors. What we're going to do is we're going to do the following. First of all, we're going to take each one of those vectors and multiply them by a scalar. So the first vector v1 gets multiplied by k1, the second one by k2, the third one by k3, and so on up to the last one. Now we have m new vectors. What we're going to do is we're going to add them all up. Of course, once you know how to add two vectors, you can add any finite number of vectors just by repeating the addition over and over again. Well, this is it. This is what linear combination is. And again, it's a very, very simple thing. You'll have plenty of opportunities to practice on constructing linear combinations of vectors and recognizing vectors as linear combinations of others. We're going to do this day in and day out. So just start from some simple exercises like the ones I've recommended from the book in class, or I will recommend in the book from the book in class. But keep in mind, this is a very, very, very important construction of linear algebra. Basically, if there is one thing you want to remember about this course is how to construct linear combinations, although I do hope you're going to remember more than that. Now, so be sure to be familiar with it. Now, notice one little thing. Where did we use the definition of vectors here? Did we use the fact that that we had two components, three components? What did we use? What exactly was used here in order to define this idea? Well, I'll leave that with you. I want you to think about it and think back and ask yourself, what did I really need in order to be able to define a linear combination? Because that's going to be a very, very important issue later on once we try to get all this stuff to become more abstract and more general.